we are finally at our last conference session, which is quantum computing. And we will start with our moderator, Andris Ambainis from University of Latvia. The floor is yours.
Yeah, thank you, Eva. So, yeah, we heard already yesterday a lot, and today also a lot about how HPC will connect or is already connected with quantum computing. But today we have the opportunity to go much deeper in this new exciting topic, quantum computing. And therefore, I invite now for the keynote lecture Mikael Johansson from quantum technology, manager for quantum technologies in CSC, yeah? And yeah, then you will tell us about HPC and quantum computing merging different computational paradigms. So, floor is yours now.
Thank you. And thanks for the organizer for having me here. It's very nice to be back in Riga. I was here last, I think it's already 8 years ago, and then it was just for pleasure. Now we mix a bit of business in here as well. So yes, I'm going to give some sort of an overview of what it means when we want to connect HPC and quantum computing. And but I first want to say that this work that I'm going to present, so it's really based on a very large team effort. So these are the persons now just from CSC who have been involved in this, and there's also some more, but these are the main persons. I think this really shows the importance of teamwork when you are trying to combine something like HPC and a completely new computational paradigm, because you do need experts from all around. So collaboration is really crucial for this to work. But I'll start with a small introduction. As said, so quantum computing has been mentioned several times here during the conference already, but maybe just a brief definition of what a quantum computer is. So it's a device that directly exploits quantum mechanical phenomena like superposition, entanglement, wave function interference, and so forth to perform a calculation. That's a very short definition of what it is. But at the same time, I think it's important to note what a quantum computer is not, and that's especially important now in an HPC conference. So a quantum computer is not a super fast version of a classical computer. It's not something that will just suddenly make all your calculations go 1,000,000 times faster or 1,000,000,000,000 times faster or anything like this. It's different. I think this is the main point maybe from this talk, if you forget about everything else. In practice, it means that it actually will speed up some type of calculations, potentially, but others it will not speed up at all. It will just be actually much, much worse than even a laptop, even when we have advanced quantum computers. Maybe a bit about the motivation why we are doing this as HPC centers. So, as said, so quantum computers will not replace supercomputers, but instead these two different technologies will merge. And this means that it is really important to stimulate this co-creation, if you want, between these HPC and quantum computing communities. And it is work that has started very well now, I would say, in recent years, but there's still much that needs to be done for, first of all, increasing the understanding and coming up with a common language between these two groups, because quantum computing is still, it was born in a physics laboratory, and many of those that are building quantum computers, and also partly the software stack there, have more of this physics lab experimentalist view on computing, while HPC is a much more mature technology, of course, and it has decades of development and standardization and best practices already developed behind it. But at the same time, our users, I'm speaking now from an HPC point of view, center point of view, will need this early access to some sort of an HPC QC infrastructure, just so that they can start making their computational modeling workflows quantum ready. And this transition from running just on classical CPUs or GPUs to quantum processing units really requires this fundamental rethinking of the problems that you are trying to solve, and of course then new algorithms. And creating these really requires lots of time, resources, and support. And here, I think that HPC centers really are a natural starting point for this to get going, because we already have all the basic services that one needs for deploying some sort of a large infrastructure for thousands of users in place. So we have the user authentication, we have heard about that, administration, resource allocation, we have heard about that here, storage, high-speed networks, classical resources, all of this is already in place. But that's the technical part. We also have this human resource in place. We have the end users. We have those that actually are using very much computational power for their science, for their research and development in industry and so forth. So we have the user base that requires more and more computing power. And that's, of course, also the ones that we want to target. Part of them, we'll come back to that later. So what is needed is that we need to have these end users preparing for this HPC QC revolution, if you want to say so. And here, this is something that HPC centers cannot do alone. So we really need the help of the end users, of universities, of companies who are developing software even, because it really requires plenty of development on the software stack, on the hardware side to get this going. It also still requires plenty of basic research, and I think this is important to understand that the quantum computers still are prototypes. There's still lots of unsolved technical problems, scientific problems that we need to solve. It's not a mature technology in any way. And one sometimes gets a bit too much ahead of oneself and thinks that, okay, now we just buy quantum computers and plug them into HPC systems. That's not really true. We really need to put lots of effort still on just developing the quantum computers themselves. But to start all of this, we need to have some sort of computational infrastructure in place, and the users need to have the basic tools so that they can get going. And that's something that is, I think, the role of the HPC centers. So the target of today is a distributed HPC QC infrastructure. And I just want to briefly mention 3 ways of connecting HPC and quantum computers, just to note that there are different ways of doing this. And I don't know, no, the pointer doesn't work. But the first one is the standalone cloud access, fits also the theme of this conference. That has the problem that is stated there, that it has a medium to high latency between the network communication between the quantum computer and HPC. Then we can fix that straightforwardly by having this co-located on-premise solution where we put the quantum computer in the same data center as the HPC computer. But we can also do it in another way, and that's a distributed way that I'll build upon today, and that's when we have the QPU and the HPC resources physically distant, but anyway connected. And these come with different levels of complexity for the software stack, and in increasing order, I would say. So the cloud access is the simplest, then co-located is a bit more work, but then to get this distributed working, so that does require a bit more effort to get it in place. So just comparing now these co-located and distributed versions, which are the ones that I would say are the most interesting anyway from an HPC-centric view. So it does require a bit more work, as said, because we need to take care of this one additional communication step between the classical and HPC. So we have this communication between the quantum computer here, this green atom symbol, and then we have this in-between server here that the role of this one is to do the time-critical things that require low latency, like keep feeding the quantum computer with stuff to do, because you don't want to have the quantum computer idling. It's a scarce resource, and you want to have it fully occupied constantly. But then we have this extra step of also connecting then to the proper HPC system. And well, we also need to do this user authentication twice. So it is a bit more complicated, so why do we want to do this? Well, the idea here is that when we have this software stack in place for this distributed system, then it's really easy or much more straightforward to add additional quantum computing resources. Because what we need is only a classical server sitting next to the quantum computer and then an internet connection to the HPC system. This really increases diversity of the quantum computing palette and inclusiveness that anyone who is willing to cooperate can also plug in their quantum computers into an HPC center. And the other way around, so then the HPC users get access to a much wider selection of quantum computers without having to have them all in one HPC center. Most HPC centers cannot afford to buy all the 20 different modalities of quantum computing, but the users actually would need to have access to all of these different ones because we don't know how they work, and different quantum computers work well for different problems. And then, well, it also then facilitates this time sharing of the QPU resources between these HPC centers, for example. So it's better to have half of 2 quantum computers than just having access to 1 quantum computer, for example. And then another point is that these quantum computers and HPC systems can be optimally located when they are separated. Now this starts running. So we have the HPCs in large data centers, which need then, as we have heard already, sufficient and affordable electric power. But quantum computers, they don't really need electricity almost at all when they are running. They are like a fridge. But they do need shielded environments, so they need to be shielded from temperature, vibrations, and other sources of noise. And one slightly worrying aspect is that apparently already cosmic radiation will disturb a quantum computer, especially when the qubit count increases. LUMI was mentioned here already before a couple of times, and I just want to highlight here briefly what we have done in this connecting quantum computers with LUMI. So in March 2022, we ran the first cross-border HPC QC job on LUMI, and then we connected LUMI with the Cal 9000 quantum computer in Sweden, the Chalmers University Wallenberg Center of Quantum Technology quantum computer. Then a bit later, we connected LUMI to the Finnish quantum computer Helmi, and that has now been up and running and in production use for 1.5 years for users, where they have been able to run jobs that use both classical and quantum resources. And next for us is to implement this LUMI-Q concept, which means setting up pan-European distributed HPC plus NQC environment where it understands that we will have several quantum computers in the mix. And the idea is to put in place a full software stack based on open source licenses. This slide was already part of Pat's presentation, but I just want to point this out that what we actually want to do is to cross-couple several quantum computers located around Europe with several HPC centers located around Europe. So in LUMI-Q, the funded project will procure 1 quantum computer that will be connected to the Carolina supercomputer in Czechia. But the idea, as said, is to build up then the software stack for operating the LUMI-Q quantum computer from Carolina in a way that's also then transferable to other places, so that it's easy to connect more resources in a way for free, because the scalable software solution has been put in place. I have no idea how I'm on time, so maybe someone shows me at some point when it's 5 minutes left. There's a few considerations that I want to bring up when we are connecting these 2 different types of systems. And one is really, I want to highlight this, that this is really a new experience for end users. So users are familiar with running, or those users that are familiar to run on quantum computers in the lab often have little experience with HPC systems. So they are just used to use their own machine in the lab and run there and not care about HPC at all. So they don't have this HPC tradition at all. On the other way, users that are familiar with HPC needs to use now a device that is really a device for experiments. So that's very strange. It was already brought up here today already a couple of times that what is required for a good HPC system is that all the results are reproducible and so forth. But quantum computers, for example, are not supposed to give the same answer when you run the same calculation twice or 3 times or 1,000 times. They're supposed to give different answers. So if it's reproducible, then there's something wrong. And this is a completely new thinking that you have to get also the end users to accept. Okay, the maturity of quantum hardware was mentioned already, but then there's this other practical thing that comes when you want to share these resources. It's easy to say, but getting it done is actually much more difficult because you need to agree between institutions on costs, on responsibilities, user access policies, and so forth. And it's not straightforward. Even if everyone is friends, anyway, when it comes down to writing a contract, then the legal departments find lots of problems. And that is something that you need to take into account that this usually takes much more time to put in place than the software to connect these quantum computers. Okay, I might skip the authentication part, but I would say that if you just take the conclusion from here, so in practice, for authentication, it's easiest if the quantum computer trusts the HPC system, so that if a connection comes from the HPC, then a quantum computer should trust that that has already been vetted. It is a legal user who has allocated resources to run on it. Otherwise, in our experience, that's the way to do it. Okay, here's then some technical details that one has to put in place if one actually wants to have this. So users should be able to submit jobs, for example, to the quantum computer without sending any sort of identifiable user information from the HPC to the quantum computer. Both for GDPR reasons, but also from just fulfilling all sorts of different security certificates and such. So we need to put this in place, and we have put that in place, but it's not straightforward either. And then one needs to put in place all sorts of these metadata schemes. You need to transfer information between the quantum computer and the HPC system. Not only consumption of resources, but also all sorts of other systems and things that you don't have to think of also when you are just using a classical research. So for example, it's figures of merit, which means that how well is the quantum computer calibrated, what are the error rates at that particular moment, because that will change from 1 minute to another, is required because many scientific publications these days require that if you submit an article, then you have to report all these, the specs of the quantum computer at that time when you run that calculation. In an HPC system, you can trust that, okay, it is the same year out. So you need to put it in some sort of automatic system for this also, so that users don't need to take care of this themselves. Then there's this step of data transfer between the two, and this is also very dependent on what kind of quantum jobs you are running. If it's only a quantum circuit, if it's a predefined algorithm, variational algorithm, or also then the most complex part, but also probably already in the near term, the most common part is that you have a fully defined container that contains the variational algorithm that the user wants to run, that you need to send to the quantum computer, or this orange box that is sitting next to it. And then depending on what kind of runs you are doing, if you are doing some measurement experiments, then you might need to send, actually we calculated this, that for some experiments, when you get up to about 100 qubits, then you are already transferring terabytes of data back from the quantum computer. So this needs to be taken into account as well. Another challenge is then user expectations, and this is not an imaginary question, it's something that we actually get asked. So now there is a question that, okay, why should we spend millions on a quantum computer that for the moment for the user doesn't do anything faster than his or her own laptop? So why didn't we use these 10 million euros to buy NVIDIAs? Because that's something I can use now. So where is this quantum advantage from the end user point of view? Okay, in some cases it's motivated by research. You need to do quantum algorithm research, for example. Then we also need to remember that we are preparing for the future. We have to start this work now so that we have all the software in place, the software stack, full software stack in place when the quantum computers really become sufficiently advanced that they start giving advantage. But we have a completely new user base also, and that's, as mentioned, so we have users that are unfamiliar with HPC, and which means also that HPC centers, we have very little familiarity with those users. So we don't really understand exactly what they want, and that's something that we also have to learn. It's not only the users that have to learn how to use an HPC system. We, as HPC centers, really have to accommodate this new type of users and not just say, go home and learn and then you come back. No, we actually have to also actively take them into account. Okay, quantum advantage, when will this come? Well, that depends really on the definition of quantum advantage. And the first and most common one is, of course, is wall-time quantum advantage, where a quantum computer can help solve something, a given problem faster than if we would use just a classical supercomputer. This is still some time away. I'm not going to even say a number here now. I will actually say one later, but no, not at this stage. That varies very much, and it's very dependent on both hardware and software development. But then we have this second one, which is green quantum advantage. And I think this is a rather important one, because here the advantage would come from the fact that one would use quantum computers or partly quantum computers to get a higher solved problems per energy used. This does not require that these QPUs would solve a problem faster than a classical computer. But as long as you solve a problem using less energy, it's already very valuable in many cases. Okay, then there's a slightly related one, the quantum quality advantage, which would mean that by using quantum algorithms and QPUs, you would actually get higher accuracy in your results instead of maybe doing the calculation faster. And this really would come from the fact that one needs to solve some given larger problem from a completely new angle and thinking of it in a completely new way. And number 4 I'll come back to in a moment, so I'll just mention number 5 here, other quantum advantage. If you think of carrots that we need to provide to the users, so for academic users, the carrot is that, well, you get scientific publications and project funding if you do quantum computing. And that's a fact. The industrial carrot, well, that would mostly, in my opinion now, involve competence development, learning how to use these new systems, and also early IP creation. You can develop a quantum algorithm now, even if it's not useful right now, but it will be in the future, and then you have the patent on running that algorithm. And that, especially for European companies, I think that's a highly valuable target that one should strive for, and not just let the big IBMs and Googles take all the IP in the algorithm development side. Okay, I have some sort of timeline of quantum advantage here. I just want to point out that this number 4 and number 5, so that's an advantage that we have already now. And to get back to the number 4 and the definitions that I had in the beginning, so what is a quantum computer also? Well, it is actually a high-precision quantum laboratory. And this is really a side effect from the fact that when one builds a quantum computer, one really needs to somehow tame this very unruly quantum world and get the quantum effects to obey instructions. And this requires that you have really precise control of the quantum states and all of this. This means that instead of, you have created this and done this because you need it to run an algorithm, perform some computing tricks. But as a side product, you have got something else. And I would say that these non-computing applications are actually something that we need to focus more on than what we are doing now. Because these quantum computers enable a completely new type of experiments. So instead of using the quantum computers to solve some mathematical algorithm, you use it to manipulate the quantum world. Here's some examples of this that have been in the press in the recent years. So this with the time crystals was a big thing at one point. So when one actually creates a completely new type of physical matter on the QPU. One has also at least claimed to create wormholes on a quantum computer where one actually, by manipulating the qubits on the QPU, create a physical state that corresponds to a wormhole. That's not solving an algorithm at all. That's doing completely science fiction type science without the fiction. One has also used these quantum devices to slow down chemical reactions, where one actually creates this chemical state on the QPU, but then by manipulating the quantum states, one can get it to go much slower. And here, the factor in this experiment was 100 billion, which means that one can really follow what happens in a specific chemical reaction. This was a conical intersection for those who know something about chemistry. But the idea is really to get this, in the end, this synergistic ecosystem of all these parts. So in the future, quantum computing is really expected to be a major driver for HPC in general. And we want to combine the best of both worlds. Okay, and there's also opportunities to work together on this novel technology. Well, here's Finland and Japan mentioned, but of course that also means that it's everywhere. It just shows that we really want to collaborate across the world here. And I want to highlight this, that we really need to also increasingly focus on taking advantage of AI for quantum computing, and not only, for example, quantum machine learning, which would be the other way around, but really use machine learning and AI for enhancing the capabilities of a quantum computer. There's some applications, but we will hear more about them in the later talks, so I'm not jump into those now. So I'll just summarize here. What we need to have is, we need to create this valuable classical support software for quantum. So quantum computing requires much more than quantum algorithms. It requires plenty of classical software development. Because this will bridge the gap between end users and quantum accelerated HPC, and there is plenty of this software development that is needed. Just as some examples, so there are now some new efforts on using these large language models for creating quantum algorithms in the first place. So we use AI to program quantum computers because it is so difficult for humans to do. Then we also, this has been done already for a couple of years, to use machine learning and AI for post-processing of the data that you get from a quantum computer. For example, error mitigation, so characterizing the noise in a quantum computer, and then in classical post-processing, enhancing the signal-to-noise ratio. I see that the chair is standing up, so I'll just finish by the last point here, that really by working together here across disciplines, HPC, AI, quantum computing, and especially end users, so that we know what we actually should be focusing on. We need a constant dialogue with the end users. So let's work together and make HPC-QC work. Thank you.
Thank you very much for this overview. So we have time for questions still. So here.
Thank you very much for this talk. My question about type of quantum computers. You're using quantum gates, or D-Wave also included into your analysis? Waveform.
I would say that yes, D-Wave and annealers, they are very much part of this. One concentrates very much these days on the more general purpose gate-based machines, but I think quantum annealers, especially if they are properly implemented, like efforts are ongoing now in Spain, can be very useful. And then there's, of course, also the quantum simulators by, for example, Pascal in France, that really can also provide this quantum advantage, and maybe even earlier than purely gate-based machines. So I think that but that just adds another complexity layer to this whole software stack, and also for the end users, that one needs to understand that there's many different ways of implementing a quantum computer. And even then, just the gate-based machines, of course, are implemented in many ways with different types of qubits. But yes, I don't think that we should exclude anything yet, because none of them so far has provided this computational quantum advantage where they solve something faster. And trying to predict which one will do it, I think is dangerous, because then you are in danger of leaving out something that in the long run would turn out to be the winning one.
Okay, more questions? No, not the case. Then, yeah, thank you again.
Thanks.
So So, yeah, as you mentioned, rethinking of new algorithms is also very important here. We have not only very different hardware, but also the software, and the algorithms are totally different, and therefore we go over to the next presentation, where Andris Ambainis, a professor of computer science in University of Latvia, and he is known for developing quantum algorithms and studying their complexity, will tell us about the name of presentation was Quantum Algorithms Research at the University of Latvia. Yeah, please.
Okay, how do I move the slides?
Here was device, probably. Yeah, forward and back.
Okay, so I will talk about the quantum algorithms that we have been doing here in Latvia. This is a part of a larger research effort called Latvian Quantum Initiative, which brings together computer scientists, physicists, and telecommunication engineers to work on quantum computing, sensing, and QKD. So if we think of applications for quantum computers, there are two types of applications. One major application is simulating physics. Another application is doing data processing that one would ordinarily do on a classical computer, but doing it faster or doing it better. And since I'm a computer scientist, my focus is on second class of applications, on using quantum computing to solve problems in classical computing that do not involve physics. And I'm leading a research group called Center for Quantum Computer Science. It consists of about 20 researchers, and there is a variety of things that we do in quantum algorithms. One of our major focuses is on quantum algorithms for search and optimization. In particular, we have developed the method of quantum walks, which is increasingly becoming a major technique in this field. We have worked on providing quantum speedups for NP-complete problems. We have done quite a lot of work on general algorithmic methods, like learning graphs and transducers. Both of those are methods that were developed in our group. And as mathematical computer scientists, we are also very interested in proving limits of quantum speedup. And generally, our focus is on rigorous mathematical work on quantum algorithms, algorithms with provable performance guarantees and provable limits of quantum speedup. And over the last few years, we have also looked into possible use cases for quantum computing on several occasions. We were part of a joint project on quantum algorithms for high-energy physics, working together with physicists from CERN. We currently have a quantum machine learning project together with Accenture Baltics, and we are looking at quantum circuit optimization, trying to compare different devices. As quantum computing is becoming increasingly experimental, we are trying to move in this direction as well, and to be a center that does both high-quality fundamental research and work together with companies and HPC centers. So today I will present a sampling of our work, various things that we have done over the last 5 years. So let me start with a new variant of quantum search. So I would call this proximity search. There are several applications of it, but the general setting is that we have some search space, and we are searching for an object with a certain property, and this search space has some hidden structure. And this hidden structure makes it easier to move in some directions than in others. There is this structure that makes it easier after checking object A to check object B rather than object C. So essentially we can reuse some of the information that we obtained while checking object A to check object B. So we have this search space, and we want to search it, and preferably we should be moving in small steps to neighboring objects. Now, classically, one way to search a search space like this would be to do random walk that moves between neighboring objects. So it would move on this search space by making small steps that would gradually result in searching the entire search space. So what we have shown is that for any algorithm of this type that satisfies certain constraints, there is a quadratic quantum speedup. One can always find a quadratically faster quantum algorithm. And the reason why this is interesting is that this is a quantum speedup for a somewhat generic algorithmic primitive that can be applied to various problems. And a second result of this nature, also a quantum speedup for a general algorithmic problem, is the work that we recently did on quantization of divide and conquer algorithms. So classically, many computational problems are solved by divide and conquer, where we divide problem into smaller subproblems. A prototypical example of this is merge sort, but this can be used in a variety of areas. And what we have developed is a quantum divide and conquer method, which is a method for speeding up divide and conquer algorithms whenever divide and conquer is used to search some search space. So, okay, to be clear, we don't speed up merge sort. There is no real need for quantum speedups to merge sort. Rather, what we do is we speed up large search problems if the classical algorithm is using divide and conquer. And there are various applications. This can be applied to string problems. One example that we had was finding the longest substring of a string where all symbols are different. It can be also solved to problems in geometry and image analysis. So if we have a set of objects and we want to find whether one object is covered by the other objects or whether one object is visible from a certain point, occasionally we can solve these problems by dividing the whole plane into regions and then dividing this into subregions and then doing search on these subregions. And what our result means is that quantumly we can do this better. And okay, here is one particular example of a geometric problem that we can solve. There's a set of lines, set of points. We have to determine if any of the points are on any of the lines. There is a quantum speedup for this that uses combination of quantum search and classical data structures. And together with Accenture Baltics, we have worked on various image analysis problems. We have looked at analysis of medical images. So the task is given a medical image, an X-ray image to determine the diagnosis. We looked at doing a classical feature reduction that reduces the image to some number of features and then doing a quantum classifier on a quantum annealer on top of that. Oops. And then we also looked at more abstract problems in image analysis, like generating images with patterns of certain type. So we have looked at doing that with Boltzmann machines on a quantum annealer. So we train a Boltzmann machine classically and then use quantum annealer to generate images. And we used the D-wave machine and we embedded a restricted Boltzmann machine of 288 bits into the D-wave annealer. Well, the annealer actually has 5,000 qubits, but due to this very high connectivity that we needed for our restricted Boltzmann machine, we could only embed a 288-bit restricted Boltzmann machine. And that is among the larger machine learning models that have been embedded into D-wave. And we are also looking at building a theoretical foundation for hybrid quantum classical computation. So it's clear that in the foreseeable future, what we are going to have is quantum computers that are capable of short quantum computations working together with a powerful classical computer. And what we would like to do is we would like to put such hybrid computation on a rigorous basis. So we are looking at strategies to transform quantum algorithms with provable speedups into hybrid algorithms. And we are looking at how to prove limits on how big quantum speedups can be achieved by hybrid algorithms. Okay, so that's roughly what I wanted to tell, and I would be happy to answer any questions if you have them.
Thank you very much. Questions?
Thanks, it was a very interesting talk. So, I was especially proud when you brought up this last one of proving the potential speed up of hybrid algorithms. So, do you have any expectations of what that will show, or the limitations of how much speed up I can get from hybrid algorithms?
Well,
pessimistic or optimistic?
Well, it would definitely vary by problem, just like quantum computers provide various degrees of speed up. Well, I think what hybrid algorithms can do will also vary by problem. So far we have looked at problems like quantum search, where we basically discovered that there is some trade-off, that but the power slowly decays as you make the computations shorter and shorter. And then that seems, I think that will probably happen in quite a few cases. And then the question is, can we find cases where it doesn't happen and where this short computation is enough?
Thanks.
More questions? Are you using real quantum computers for your research?
Occasionally, yes. We did experiment. I mentioned our experimentation with D-Wave and Euler, and then we have also run experiments with circuit optimization, optimizing particular quantum circuits, and we have also just played around with trying to make some of our algorithms as small as possible and seeing whether they can be reduced to instances that are small enough to be run. And I think we plan to be doing more and more of that now that quantum computers are available. I think we will definitely use this EuroHPC quantum computing infrastructure that is coming up.
Okay. So, last chance? No. So then, thank you, Andris, again. So, and then we will move from from Latvia to Denmark. And the next talk is a deep dive on Denmark's quantum landscape and the roadmap for coming years. And Henrik Sønderskov, Denmark, please introduce yourself a bit so I have no information.
Okay. Well, thank you very much, and thank you for having me. My name is Henrik Navntoft Sønderskov, or in Danish, Henrik, as we say. I am the new head of quantum in DK, and I will get back to that in a minute. So, but first of all, I will just say again, it's very nice to be here. So thank you for the invitation. This has been quite a long day. So I just out of curiosity want to ask: is anybody sleeping here yet in the room? No. Everybody is agreeing on not sleeping. That's good. No, I think this has been just allow me to say, I think this has been a very interesting day, and also interesting day yesterday. I think I'm gonna need a supercomputer to sort of like process all the information having received by now. So I don't know if Loomis is somewhere around here to help me with that later on. But definitely a lot of new information for me. I must also tell you that this is not my first time in Latvia. I've actually been here quite a few times. I'll get back to that in my conclusion, but I think it's very necessary to say that this is all about collaboration, really. And I might add as an introduction that Denmark has had diplomatic relations with Latvia since 1921, in case you didn't know. And we do have a lot of similarities. You have an old flag. We do that. We have an old flag in Denmark as well. Actually, the oldest flag in the world. Latvia is second on that. But also we have the connection regarding quantum. And Latvia, in case of those of you who do not know that, signed a declaration of quantum collaboration on the 22nd of March, together with 20 other European countries, Denmark included. Yeah. Now, as for a deep dive, this is obviously not going to be a deep dive because I only have 15 minutes, so it's a quick dive. And you must bear with me, I'm new in this position. I have only been in this position for 1 month. Previous, I've been working 17 years in the Danish defense system, also with disruptive technologies, but I'll get back to that too. So that's for an introduction. I'll tell you a little bit about the Danish quantum ecosystem as we see it by now, which is in rapid development. And I'll also give you a little bit of insights as to where we're going in our perspective. And then I have a conclusion. Okay, so as my colleague Eske, who you heard earlier today, said, we are part of DK. DK is a consortium under our Ministry of Education and Science. So really our board of directors, if you may say it that way, are members from the various Danish universities. There are 8 universities in Denmark. So we are a consortium doing national research infrastructure. That's the original mandate. Now, I'm not going to talk too much about DK because Eske already mentioned it, but I might add that, as you can see here, I just highlighted it here, that as from 2023, there was a new focus in Denmark regarding quantum technology, as our government made a national strategy regarding quantum technology. If you haven't read it yet, I can highly recommend reading it. And you're most welcome also to give me a call, and I can send you an English version of it. But basically, and I'll get back to that too, basically what that meant was that DK was appointed of having a significant part of that strategy regarding infrastructure. And that's why my new department in DK was established, really. So we're just starting up, but we are full speed ahead. So as you can see, just shortly giving you the frame of DK, we have Eske sitting here, and we have me sitting here in our 2 departments regarding HPC and quantum. So what do we do? I'll tell you what we do, and I'll tell you afterwards why we do it. So really, I had some good discussion with Andris yesterday also regarding access to quantum computers, which is at this point, we talked about them as basically not in a funny way, but as toys at the moment, because we have so many different technologies emerging from various ways of evolving quantum computers. But basically, one of our...
Excuse me, can you hold so?
So basically, we have a field we call Q-axis, which basically is about finding out what the needs are from especially the Danish universities in order to have access to various different quantum computers. So that's an effort in itself. Then we are and have been building a Q algorithm, as we call it, but that really is an academy for quantum algorithms. And what does that mean? Well, that means that we each year put out calls for PhDs and postdocs, so people can apply for funding through DIKE for various quantum algorithms. And thirdly, in the middle, we have what we call Q competences, which is basically about education. Education in every layer. And this is where it gets a bit tricky, because DIKE is about IT infrastructure for the universities, but basically we also do not have to forget public administration and industry. Lastly, we also participate in the European EuroQC project, and we, of course, are part of the LumiQ consortium. So, this is basically the strategy I was talking about before, the national strategy. And it really has two parts. One of them is about the research and innovation ecosystem and a long-term strategic investment. And as you can see here, down at the tree here, the access to digital research infrastructure, that's where DIKE come in. And some of you might see, well, this is a tree regarding the strategy, but what you can see just ahead of that is the security sector. Why do you think that's there? Any good suggestions? Anders, you have a suggestion? No. Well, on line 13 in the paper, it says that you have to acknowledge that this is about security. I'll skip ahead of this. So, Denmark aims to have one of the world's leading quantum research environments and to have the ability to effectively translate research into new usable technology. And this is where we really see it with our different ministries. We have EU and we have NATO too. And why do we have NATO? Well, part of the initiative is also to have security. And NATO has established the program called DIANA. Do you know about that? Yeah. It stands for Defense Innovation Accelerator of the North Atlantic. And that's the biggest defense system for innovation that the world has ever seen regarding NATO. And guess what is on top of their list? It's quantum. Quantum and AI. So here we have it. In Denmark, we have quantum branches going from science, commercial, in every sector, and the political level. So, when we talk about the Danish landscape of quantum, this is just a small fraction of who are conducting quantum-enabled technologies in Denmark. And I must say that you have to quickly forget this picture because it's evolving as we're speaking, so to speak. Now we see some, of course, the defense sector, the research and innovation sector, the banking sector, but really in Denmark, we have a little bit more than 100 actors regarding quantum at the moment. 100. And I can tell you that for about 3 to 5 years ago, I don't know, I didn't make the calculation at then, but I can tell you there weren't that many. There were maybe only a few. So, I want to skip to the takeaways. In Denmark, we see quantum as an enabler technology. It's made possible, of course, obviously, as we have been seeing, to break out research. But in Denmark, it's largely driven by the private market and investment from political strategy. The political strategy on this matter is 1.2 billion Danish kroners. So that's quite a lot of money in Denmark. The roadmap from here, we're going for a unified, complex Danish ecosystem. Moving and evolving targets is a general picture of quantum right at the moment because it's ever evolving and it's really innovating. And the geopolitical situation marks the frame for the future. So that's the only way to go ahead to collaboration. Any questions?
Questions? No, not everything clear.
Okay.
Yeah. So thank you. Thank you again. So the third presentation is cancelled. Yeah, this the Nordic region, a quantum life science powerhouse by Eva Carboner due to illness. Yeah, unfortunately, and therefore we are going over to the last presentation from Andreas Wierse. Welcome again after very interesting talk yesterday. Yeah.
I don't take it personally.
About very practical industrial applications. Now we are going to totally different field. Yeah, so please, the floor is yours.
Yeah. Thank you. Well, I extra put my ETP for HPC shirt on, so Anders said that's one of their bosses. Yeah, so I'm now between you and the weekend. Sorry for that, but I'm also here in a kind of undercover mission. If you remember correctly, yesterday I had a different affiliation, Seagrass BW. I'm here now presenting the project EuroHyPerCon, or the study as far as it's already available. The better expert would have been Fotis, but unfortunately he could not be here, so they asked me to take over, which I will do, and I will try to do my very best. So a fact sheet for EuroHyPerCon. It's a study for hyperconnectivity for HPC resources in Europe, as you can imagine. It's funded by the joint undertaking. It's about, well, more than, about 3/4, so there are kind of three months left, so 2/3 actually. There are 3 partners: Innovex, where Fotis comes from; HLS, where I'm affiliated in a way; and Enomics. There's also a website for this, so if you want to have further information. So what is this about? The idea is to have a hyperconnectivity service specification, including an implementation roadmap for a secure, federated, and hyper-connected European HPC and data infrastructure. So this is kind of a requirements analysis and a design for a network and services. And there are basically 2 parts. There's first the needs, how do you say, to find out what the needs are, to do an analysis of the services. So there's engagement, or has been engagement, with the communities. There's still something possible, but a lot has happened already. So things like traffic capacity, availability, network architectures, etc. And then there's a forward-looking solution. So based on the needs analysis, an idea of how this could look like will be developed with, well, scientific instruments, AI, progressive, flexible solutions, so to be prepared for the future. And this is the tender that was used to ask for proposals. really important, there's already, of course, connectivity between European HPC centers. They are all connected already today. And Géant, we've seen them here yesterday and probably also today. Of course, they play an important role. We have the national research and educational networks that are all there. And it's not about kind of replacing them, but it's kind of leveraging them, how to prepare everything for the futures. And this is about complementary connectivity, so it has to align with what's already there, what's working and what's successful. There's a focus on federation interoperability, so that's probably something specific European, but there are many countries that have to be kind of coordinated, while communication actually in that sense does not really know any boundaries, and we want to cooperate. And there's supposed to be a collaborative study approach, so it's in a cooperation with all those who are concerned. And the methodology, I won't go through this in detail, but has been or still going on a stakeholder consultation, and there's a needs analysis that there will be kind of iteration between ideas and then check again whether the needs are fulfilled. I guess that's what's mostly going on right now, and then there will be kind of specifications and finally an implementation roadmap. So there have been needs workshops already. I think they are all finished. As a stakeholder, you might give some input still, and then there will be, I don't know, this is only one workshop probably, a progress and roadmap workshop where if you are kind of involved, I'm pretty sure you'll be able to participate in that as well. So stakeholders are all that are kind of involved here. They need to be identified. There are different classes, the providers, the users for HPC, the network providers, of course, and then also data providers and AI users, other stakeholders. You can probably discuss whether HPC users and AI users actually, are they so different? But that's the way it was set up. And of course, data related to a network plays a much more important role than probably algorithms at that point. So I think it's quite okay. There has been an online registration form where they could, they still can, register themselves to be kind of part of the overall game. And I mentioned already the EuroHPC hosting sites are of course involved in the core, but also other European national HPC systems are welcome. The users, of course, especially big users with respect to data. Destination Earth has been already named several times, but there are others as well. And then Géant and the Enrons, and then finally everybody who has deals with large amounts of data. So here you can see what was going on. So workshops that already took place. There were focus groups and interviews, so detailed interviews that had been carried out until not too long ago. And right now they have a stakeholders database without about 500 stakeholders, 680 entries, because some are probably involved in more than one. And the sites you see, the 165 hosting providers, 175 users, 130 data providers and AI stakeholders. So as a stakeholder, you can still register. So probably, go where you think it fits best. If you look at the landscape, it's kind of, it varies. So here, Latvia, for example, there still somebody could probably get in there to be represented. So providers, there's a kind of agglomeration with Germany and France, but we would like to cover everybody actually who's kind of involved there. And the picture for users is actually a little bit different, quite interesting. Well, the Baltic states together have more than Germany, so that's kind of funny. So I think there's still some place for new stakeholders to register in order to get a better image, to represent really almost everything. And down here is the link now. So it's actually pretty easy, t.ly and then E5FE8. So please feel free, if you're not there yet, please let us know and join. And there's a kind of stakeholders mapping. There is this Notobot tool, which you will find when you register yourself. So there are different areas. So this is all the tenants. For example, there's the Barcelona Supercomputing Center, Chinica, and all the others that you might expect. There's location, which is pretty important when you're talking about physical cables, fiber, whatever. And then there's, of course, also the devices that are there. You see even UK is included, Archer there from Edinburgh, because that also is really important if you want to have a balanced network, you need to know how much is happening where with how many systems. So this mapping, I think that's probably from 2 weeks ago. So there are some, some are missing. This part of the map, actually, you can see these slides have been prepared for the HPC summit in Antwerp. I tried to create one showing the Baltic region, but I didn't get access to that, so you have to bear with me. But I'm sure there are also some dots up there in the part that has been cut off. So the questionnaires right now, there had been 165 full responses, many more partial, but not all of them useful. Again, here 111 users, 32 providers and 22 network providers had participated. The initial deadline was in January. More inputs have been received, AI stakeholders, so they are working iteratively. So you can still, end of March, now closed, sorry, not for this one. And you see down there what's been submitted. So now they are analyzing this feedback, the questionnaires. So what's already been identified is there are considerable cross-border needs for operational EuroHPC hosting sites. Some countries that are more active have of course more responses, and other countries could have benefited from more answers. So that's somehow to be taken into account to balance that correctly. That's a problem with the studies where you cannot really not identify but determine the ones who should respond. So we have to kind of balance that. And there's also input from other means. So all information is welcome, and we try to collect that. Here's a few statistics. So some are not so surprising. For example, most data transferred before, during, and after executing. So if you are talking HPC, numerical simulations, you usually have some boundary conditions and an initial geometry. And then if you have time-dependent solutions, you have much more data in the end. There are also other algorithms where you have huge data, and then the answer is 42 or something like that. But in general, after is still most. This probably might change a little with AI. That's going to be seen. Quite surprising, and I was not able to identify what's really meant here, what the question was. Security requirements, something like 10% yes, almost 90% no. I doubt this a little bit. This depends probably on the question who you asked or whom you asked, because I'm pretty sure this has also been discussed yesterday and today. Even for researchers, security is an issue. So I don't know the exact question that's been behind that. Then type of HPC usage now. So there's a lot of EuroHPC funded HPC centers. There are the national ones, and then there are regional, sub-region, not on the national level, but a little bit smaller. Expectations for 2030, also not surprising. There will be much more JU-funded HPC providers. The number of national HPC centers is not expected to change much. Also similar with the sub-regions. And some people said they cannot look into the future, which I also partially understand. So the basic thing is here that those new EuroHPC-funded, JU-funded HPC centers will have to be taken into account. Then the HPC usage time frame. So most of the users that replied use it daily or weekly, which kind of is also to expect. The amount of resources used, you see it's here between 15,000 and 80,000. Probably it's node hours, I don't know, because 80,000 nodes, I think there are not that many systems that are that big. So let's assume that it's node hours, which kind of makes sense. So there are not so much of the smaller ones, and there are not too many of the really large ones. Some here are probably the extreme scale, but mostly it's kind of mid-size. And of course, this has an effect on the amount of data you have to transfer. And this is again some that says work in progress. I won't go into the details, but they look at the data size. So you see here it's 1 gigabyte to 10 gigabytes. It's a typical, a little bit larger, 100 is fine, up to a terabyte, and then it goes down again. Data transfer times, it's most of them less than 30 minutes, and this is 5 hours here. And then, well, satisfied with data transfer times, neutral, satisfied, very satisfied. That's not bad. There's only a very small, well, 10% probably who are dissatisfied. So we are already starting at a pretty good level. And then there are some expectations regarding the data size growth. Yeah, well, that's, I get public knowledge kind of. So the summary of the preliminary findings, actually the users are already quite satisfied, which we've just seen, by the services that are provided today by Géant and then the entrants. They are ready also to upgrade access and backbone links, reaching 400 gigabit per second and even terabit per second levels. So soon 400 gigabit for backbone user access. SSH access may affect network performance. Encryption can slow down how much data you can pipe actually out. So that are things that can and should be addressed. Also regarding security practices, some harmonization is needed. So obviously the JU systems will probably play an important role there because there it's easier, but also the others should be interested in kind of having the same, at least comparable level of security and practices. And let's see down there. Yeah, so mostly Géant can satisfy what's needed, and then there are some champions which was really a lot of data, transferred a lot of data. Their bespoke solutions may be required, but that's already quite positive results. So the way forward, what will happen? So there's the idea of an end-to-end solution, leverage Géant entrants, that's what I already said, bespoke solutions for big users, data providers. What's quite interesting also, one should try to connect in a good way to external cloud providers. So we cannot just pretend they are not there. They are there and they will stay. Commercial users, of course, are there a lot, but even sometimes research users use Amazon or whatever. So it's a good idea to kind of connect them pretty good. And the idea is to aim for as a service solution, so outsource to the network providers so that the JU will just have a coordination perspective and no need for an internal network management team. And then it should be kind of integrated. So go to an EuroHPC ecosystem, what I just said. And so this has been validated, the hypothesis. So there's been a techno-economic analysis of different solutions. I won't go into the details there. That's, I think they will have to find a balanced way depending on what they have in the end, how to combine this and make this as user-oriented and efficient as possible. So conclusions and next steps. So the identification is performed, but the link I showed is still open. The needs analysis going on. There will be a gap analysis to kind of then try to fill the gaps. Alternative solution designs are developed, and this analysis is still ongoing. And in May there will be a validation workshop. One online and possibly one also face-to-face at the ISC. So if you happen to go to Hamburg, then it might be worthwhile to put that on your agenda as well. Well, and I hope you don't have too many questions because I'll try to answer them, but sometimes I guess I have to just take them with me and have them answered later. Yes, please.
Very simple question. Is it possible to know which of the 8 reported stakeholders in Sweden are? Because I distributed the survey, but
I think this is not a secret because you've seen the dots. I think that would be on the map. Send me an email. I will put you in contact with Fotis. I'm sure he can kind of give you the information. Yeah. That shouldn't be a problem. I don't think it's a secret. Yeah. Mm-hmm.
Okay. More questions? Ilmar?
I have a question. Why this research is done? So what is that reason, the main reason? Can you tell us?
Well, I have an assumption, but it's definitely not public. As I said, there is Géant already. There are the NRENs already. There might be a political background to just put them on the test stand, see how they are doing, try to find what's been done, what could be done better. I personally don't really know, but it must be some political reason, because in my understanding, that actually is working pretty well. It can always be improved. Probably this is the tool to get an okay to do more. Yeah, but I can only, I really don't know. It's just guessing. Sorry.
More questions? No. Yeah, then thank you, actually all speakers of this session again. Thank you. The last session, and I will give the microphone to Eva back.
Thank you, Jānis. So we have come to a conclusion of the conference, a closing. So I would like to thank you all for coming here in Riga, and thanks to all the colleagues who helped to develop the program in Sweden, Finland, Denmark, Estonia and Lithuania. Without you, it wouldn't be possible to have this wide spectrum of topics covered. Yes, a special shout out to all the volunteers who helped during the process to set everything up and guide you where needed. And lastly, thanks to all the presenters, keynote speakers and panelists for the great interaction that we had for the last 2 days. And thanks to all the media people for covering the video for all the presentations. You will be able to receive the recordings later, maybe next week, maybe sooner, we'll see. But we will definitely send out a link so you can watch some interesting parts yourself, or forward it to your colleagues or other people interested in the topics. And photographs from the event also will be available, so let's wait for that. And now maybe Ilmars would like to have a few words as well.
So, thank you. Not so much people left, but it was a good event. And really, it was said already, thanks to many who have joined the conference and who have done the work and so on. But I would like to remember that the first such conference happened in 2012, the second one in 2013, and the third one in 2015. Now we are almost 10 years past this way due to the COVID and so on. But it was, I guess, a very interesting event, very well organized. And I hope that we will do the same maybe next year. So that's our plan. But the main thanks to all the team, what already Eva said, and my thanks, great thanks to Eva, who was organizing all this, starting from the, I don't know, September or even earlier last year. And all was done very perfectly. So thank you, Eva. So, I was happy that you are here, and now I wish you nice walk around and going back home safely, and see you somehow next time. Thank you.